top like this. So the first moment of area cannot cross the what? Cannot cross the centroid, right? So down here we know that, okay, the first moment of area cannot cross the centroid. So if you think that this is where your Vy is, right? So you have 5.0. Okay, I have to follow Vy. So you start shading the top and shade the bottom, and you start shading the top. You start doing this. Okay, this is my area of concern, right? This is wrong because we are breaking rule number what? We are breaking one of the rules. Okay, so we are breaking one of the rules that we are breaking. So if you go back to here, I know these rules are very communist, okay? You break them, you go to jail. I know that, okay? Or you don't get marks, right? I know. So this you can see, first moment of rule number 4. The first moment of area, okay, cannot cross or intersect the center. If you take where I've just shaded that region, the answer will be what? Wrong, okay? So now you have, okay, so the first moment of area cannot cross, right? Datum is at the centroid. The analysis will start from where? This is the analysis direction, right? So this is the area that you have to consider. Okay, that is the area you have to consider. Okay, so when that's the case, now you can start calculating your first moment of area. So as I said before, right? So the easy thing is what? The rules that apply, that I force you guys to apply, that is less confusing. So now you write down again, Vy over Izz, right? Qz divided by T, right? So very straightforward. Rule number 1, V and I are constant. So you don't need to worry about them, okay? So this is equal to 90 times 10 to the power 3 Newton. Izz is still constant, right? Rule number 1, we apply rule number 1. So it's 5.8133 times 10 to the power minus 6. Then the thickness is equal to what? Left and right, 2 multiplied by 0.02 again. Okay, and then from here, right? From here, we will find your QZ. Right? QZ is equal to AY bar. Right? So the area is equal to what? The area, the width is 0.02. Right? The thickness is the depth is 0.03. Now the next thing we have to find is find this distance. Right? Find the distance from here to here. Right? So we know that the entire distance, right? We are aware that the entire distance from here to here is 0.065. Right? We are aware of it. And then we know that the distance from here to here is 0.015. Right? So from there, we can find that our Y bar is 0.065 minus by 0.015. Right? So this is your so-called your Y bar now. Okay? So this will be equal to 0.065 minus by 0.015 times by 0.03 times by 0.02. So this is equal to 30 times 10 to the power minus 6 meter cube. Okay? So 30 times by 10 to the power so 0.065, 0.03. Oh, I make mistake. Left and right. Sorry, people. Okay, so don't forget, it's left and right. So it will be equal to 60 times 10 to the power minus 6 meter cube. So from here, immediately is your shear XY at point B is equal. So V will be equal to 90 times 10 to the power 3 with 90. And then VQ is 60 times 10 to the power minus 6 divided by I 5.8133 times 10 to the power minus 6. And then thickness is twice 0. Okay. So this will be equal to 90 power 3 times by 60 power minus 6 divided by 5.8133 power minus 6 divided by 2 by 0.02. So it's equal to 23.222 All right, 23.222 times 10 to the power 6 Pascal. Okay, so if we use this distribution equation, okay, so if we go and use our distribution equation, so the distribution equation is this number over here. Right. So if we apply the distribution equation, okay, using the distribution equation to find, sorry people, I think I should not rush. Distribution equation. Right. So when we use this, so we have shear xy. Right. So now we want to find. So if we look at point B, right, y is equal to what? So the distance from y to here, right? So the distance from here to here is equal to 35 millimeters, right? So this will be equal to 0.035, right? 0.035. So when that's the case, the shearing stress at point B will be equal to 32.705 times 10 to the power 6 minus by 7.7409 times 10 to the power 9 multiply, okay, I don't need this anymore, 0.035 squared. Okay, so from here 32.705 power 6 minus 7.7409 power 9 times 0.035 squared is equal to 23.222. Okay, both are the same. Okay, so this is a very good learning examples. Okay, it's not just, it's very easy to do. Okay, it's very straightforward. Is the outtake of this is what does those equation means? Okay, what does those equations mean? And you all will have the confidence, right? You all will have the confidence to find anywhere now, right? Anywhere at point A, point anywhere of the beam I ask you for the shearing stress, you should have the confidence. Okay, so remember when you are doing statics and dynamics, you always calculate the what? The average. What do I mean by you always calculate the average? You always go for force divided by area, right? It's an average you're calculating. For this, we are calculating very specific point. We are calculating the what? If you look at this, you are calculating the distribution. Okay, you know at every point of this structure what stress you get. Because on detailed design analysis, you need to know where the maximum stress is, not just the what? Not just the average. Okay, because the maximum stress is going to kill your what? Your structure. Like for this case, maximum stress, shearing stress is important. In real life, where it will fail, it will fail at the where? It will fail at the joint. Why it will fail at the joint? Because you have what? Stress concentration. I'm not going to teach this in this course. So those of you that are doing manufacturing program, when you do your machine to design and manufacture, they teach you that. Okay, from here, I'm just teaching you the fundamentals on how to analyze the stresses. Anyway, to calculate the safety or stress concentration is just a multiplier. Okay, you still need to know your fundamentals based on this. Okay, so those of you who are in civil engineering, there are at least 2 or 3 courses after this that you need this work. Okay, and if I have any complaint from the instructor that my students cannot do shearing stress distribution, I'm going to come after you. Okay. All right, I'm teaching you so that you can do well for your next course. Okay, That is better. Right. So now the next thing is we are going to look at longitudinal shear of a beam section. So this is a new topic now. Not new topic, a different section. Okay. So we are going to analyze, right? So we're going to analyze right the strength the strength of the joints under shear loading or shear force. Okay. So the joints right, the joints can either be glued, okay, bolted, screwed, okay, nailed, name it, we do it. Okay.
Are we going to analyze welded joints as well?
No, we're not doing welded. So welded joints, those of you who are doing manufacturing, is under machine tool design. But again, come back to here. Same principle. Right. So if we have a section now, here we have a section now. By the way, wait. Let me draw for you there. I'm too excited now. Okay, wait. I so love to teach this course. I'm teaching another course that some of you are doing with me in manufacturing. I hate that course to the core, man. I'm dying in that course, but this one I'm so excited. So anyway.
Which course is that?
Manufacturing.
No, the course name.
3CO3 or 3MF3. I hate that one, but anyway. So over here, right? So we're going to determine. So this is a structure that we have, and we have different loads. So let's say we have a load down here. For example, we have a load P down here. Okay, we have a load P down here. And this structure, if we're going to look at the cross section, NN. Okay, so we're going to have I'm going to draw the cross section. Okay, I'm going to draw this cross section now. So the cross section will be, so this is a transformation, right? So this is your, now this is your Z, and this is your Y, and then this is your rotation in your X direction. Okay, and then this is a cross section. Okay, so cross section view of NN. Right? So this is how the structure look like. So the structure is made of different sections. One over here. Then you have another beam look like this, right? Then you have another part look like this. Okay. And then you have another section look like this. Okay. And all this, right? Where this will fail. So these are separate parts. Okay. So this is made of one one part, 1, 2, 3, 4. And the way you join them is you can either you put nails or bolts. So where the green line represent, okay,